Hello everyone, and welcome to today's webinar on application of EDS and EELS in analytical TEM. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Dr. Jeff Wang, Senior Materials Scientist, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our presenter, Dr. Xiangyu Xia, Manager of TEM Imaging at Nanolab Technologies, a Eurofins company.
Thanks, Rena. And hello, everyone. Welcome to today's webinar. The topic of today's webinar is application of EDS and EELS in analytical TEM. So EDS is for Energy Dispersive X-ray Spectroscopy, and EELS stands for Electron Energy Loss Spectroscopy. So both of them are commonly used techniques in TEM, transmission electron microscopy. They're mostly used for chemical analysis. So today's talk will be focused on chemical analysis in TEM. So first, a little bit about myself. My name is Xiangyu Xia. I'm currently a project manager at Nanolab Technologies. My specialty is on materials characterization using the combination of electron microscopy, spectroscopy, and atom probe tomography. So today's outline. First, I will give an introduction to our company, the Eurofins Material Science and Nanolab Technologies. And then I will give an introduction to the Smart Chart, a summary of technical services we provide at Eurofins Material Science. And then I will jump into the main topic, starting with the basics and fundamentals of EDS and EELS. Then I will discuss a series of application case studies, including a reverse engineering materials analysis study of 7nm FinFET and 3D NAND technologies, and then some STEM use studies on some other materials. First, about Nanolab Technologies. We are a third-party external service lab. Nanolab was founded in 2007 and joined Eurofins in 2018. Now we are a member of the EAG Laboratories or Eurofins Material Science. Overall, we have around 80 employees, and more than half are technical engineers with advanced degrees. We serve a wide range of industries, including semiconductor equipment, semiconductor material, automobile, LED, batteries, consumer electronics, and of course, academia. We lead the materials service lab industry by providing high quality data at fast turnaround time, and we try our best to protect our customers' IP. Our services include advanced microscopy, including SEM, FIB-SEM, TEM, and other TEM-based techniques. And also we do atom probe tomography to provide three-dimensional elemental analysis at atomic scale. We also do physical and electrical field analysis and surface analysis, such as SIMS and XPS. Here is an overview of our tools. In the center here, you can see this one is a CS probe corrected thermofacial titan. So this tool can provide ultra high spatial resolution up to 0.7 angstrom and equipped with EDS and EELS capabilities for chemical analysis. So some introduction about our sister lab, EAG Laboratories. We have over 600 employees all over the globe in Europe, Asia, and North America. We, the Nanolab Technologies, is here in North California, but we worked all together from our colleagues all over the world with diverse backgrounds to help our customers on their materials analysis problems. So here is a summary of analysis we provide at Eurofins Material Science, called the Smart Chart, or the Spectroscopy Microscopy Analytical Resolution Tool. So the x-axis here is a spatial resolution, and the y-axis is chemical concentration. There are two kinds of chemical concentrations, either by atoms per cubic centimeter or relative composition. By looking at this chart, so if you want to know about a certain technique's specification, just find the corresponding bubble on the chart. So it's also called the bubble chart. So for example, if I want to know about dynamic sims, then I just find the bubble of dynamic sims here, and I can see the x-axis, the spatial resolution around a couple of tens of microns, and the chemical sensitivity could be up to 10 ppt. If I have a materials to analyze, but I'm not sure which technique I should use, I can also use this chart. For example, my smallest feature is, say, around 10 micron. So 1 micron spatial resolution should be well enough. And then I know roughly my lowest concentration is around 5%. Then I know 1% sensitivity should be enough. So then I can locate the technique to be here and here. Then the right technique for me should be SEM EDS. So this is how we can use this smart chart tool to help us with our materials analysis questions. Today, the talk will be focused on TEM-based EDS and EELS. So this bubble. You can see here that this bubble is the leftmost bubble, so it can provide the highest spatial resolution up to 0.7 angstrom, and also the chemical sensitivity is up to around 1 atomic percent. Here, just some basics about TEM. We provided 2 webinars on TEM recently. One more general discussion, and the other one TEM application in crystallography analysis. Please free to check our website for these recordings. Today, we will just give a brief introduction about TEM, and we will not go into too much details about TEM, imaging, sample preparations, etc. In TEM, we have an incident electron beam. The beam will transmit through a super thin sample that is around 50 to 100 nanometers thick. The transmitted beam's intensity is related to the sample material's mass density or atomic number or crystal structure, chemical compositions, etc. So you can analyze the transmitted beam and analyze the sample material. So this is a brief configuration of a real TEM, a thermal Fisher Titan. You can see the correspondence between these 2 pictures. This is an electron gun. Here are a couple of lenses and emitters to condense the beam. And here is a TEM sample. Here are detectors and cameras to analyze the beam. Here are some typical TEM data. Here, this one shows the STM image of a silicon film. You can clearly see the silicon atoms dumbbell and some atomic level, nanometer level high-k metal-gate layer. You can easily do sub-nanometer measurements. Here, this one shows the grain orientation mapping of tungsten word line in 3D NAND. So you can clearly see the nanometer level grains, the grain size, the grain orientations, etc. Here shows the STEM EELS analysis result of the chemical distribution of 7 nanometer FinFET technology, which will be the focus of today's talk. So first, some theoretical background for us to understand EDS and EELS. In EDS, we are analyzing X-ray signal. So the incident beam interacts with the sample material and it excites inner shell electrons and leave holes behind. The outer shell electrons would fill in these holes and emit X-ray. This X-ray signal will have several characteristic peaks that are directly related to the chemical species in the material. So you can analyze these peaks' energy, position, and relative intensities and get to know what kind of element you would have in the sample material and what their relative concentrations are. For EELS, there is a incident beam as well, and there is a transmitted beam. So we collected the transmitted beam and analyzed the energy difference between this transmitted beam and the incident beam. This is called the energy loss. This energy loss, again, is related to the chemical species of the material. So we can analyze the peak, or we call it edge in EELS, or the edge of the edge position and relative intensity of these edges, and analyze the sample material's composition and relative concentration. And also, this energy loss is directly related to how the elements are bonded to each other. So we can use EELS to analyze the bonding information in the sample material. So this is how EDS and EELS are integrated in a TEM, schematically, of course. So here is the electron source, and you have the electron beam condensed by a couple of lenses, and then interact with the sample material. the X-ray signal would emit from the sample material. So we have EDS detector around here. So this shows a typical EDS spectrum, and you can see the characteristic X-ray peaks of cobalt, iron, silicon, etc. And in EELS, we can collect the transmitted electron by this EELS spectrometer and analyze the EELS spectrum for each element as well. Now let's look at some specifications for EDS and EELS. For EDS, the energy resolution is around 130 eV. So the distance between two distinguishable peaks in EDS spectrum must not be smaller than 130 eV, or you will not be able to differentiate them. EDS generally works better for heavy elements such as titanium, iron, cobalt, chromium, etc. Generally, light elements such as carbon, nitrogen, oxygen would result in a larger error range in quantification results. And for elements lighter than carbon, such as lithium or boron, most of the time you will not see anything meaningful. Sometimes you may see some boron or lithium peaks, but the quantification results would be very unreliable. So in general, we would not use EDS to detect anything lighter than carbon. One EDS scan can give you a full X-ray spectrum, so from 0 up to 40 keV. So it can cover almost all the elements in your material, of course, not including the super light elements. So this is especially useful if you want to analyze something with an unknown composition. So you have no idea what your material is, and you want to have a brief understanding of the element, then you want to start with EDS. The chemical sensitivity of EDS is around 1 to 5 atomic percent. The exact number here also depends on what kind of element you're looking at. So about EELS, the energy resolution is much higher, around 1 eV. So it really helps if you would like to see more details of some selected element. It is more sensitive to low Z element, the light elements, such as lithium, boron, carbon, nitrogen, oxygen, etc. Actually, we will have another webinar in the next month from my colleague Jiangtao Zhu, focused on characterization of lithium battery by EELS and STEM. So please stay tuned. EELS spectrum is bonding specific. So here I show the carbon EELS spectrum. You can clearly see that all three are all carbon, but in three different forms of graphite, fluorine, and diamond. They show very different EELS spectrum shape. So, but if it were in EDS, you would just see one carbon peak, no bonding information like this one shows. EELS generally has less artifact compared to EDS. For example, in EDS, you can always have background noise from either TM grid, TM chamber, etc., such as copper, moly, zirconium, iron, etc. So EELS can help avoid this issue. The detection limit of EELS is also around 1 to 5 atomic percent. So one question that we are always asked by our customers is that, should I do EDS or EELS? And the answer is never easy. It really depends on what kind of material you're working with and what your analysis purpose is. So it is really important that we talk this first before the analysis. So here is a very brief summary of EDS and EELS, their respective advantages and disadvantages. So generally speaking, EDS works well for heavy elements. But if you're working with light elements such as lithium, boron, carbon, nitrogen, you might want to choose EELS. One EDS scan can give you a full X-ray spectrum, so you can check almost all elements in your sample material. But EELS analysis range is relatively smaller, so it is more suitable for selective elemental analysis. So you better know what you are looking at before EELS. This feature makes EDS very suitable to detect unknown materials because you have no idea what you are looking at. So you want to use EDS to start. For some specific elements, EDS or EELS might work better. For example, fluorine or chlorine. They are commonly elements of interest in semiconductor industry, or when people try to analyze wet edge residues. So they often combine with oxygen, carbon, or silicon. These elements, the carbon, oxygen, and silicon, their EELS spectra will affect analysis of fluorine and chlorine by interfering with the signal background. So we would recommend to do EDS for fluorine or chlorine. And for some group of elements, they have peak overlap issues in EDS. So for example, the tungsten, silicon, hafnium, tantalum. The EDS software can do deconvolution for these peaks, but we would still suggest to do EELS to double check these elements. And also EELS has some other benefits, such as bonding analysis. It can avoid some artifact issue, and it can be used to analyze a band gap, thickness of the TM sample, etc. Now we have some very basic understanding of EDS and EELS. Let's look at some real-world industrial applications. We will start with a reverse engineering materials analysis study of a smartphone with focus on 7nm FinFET technology and 90+ 3D NAND technology. FinFET, thin field effect transistor, is probably one of the most important technology inventions in recent years in semiconductor industry. Compared to traditional planar CMOS, 3D FinFET enables faster switching times and a higher current density. So it enables Moore's law keeping moving forward. This complex 3D structure includes source, drain, gate, and fin. So electrons would follow this path and is controlled by the gate here. So as technology advanced, the dimension of the FinFET keeps going smaller and smaller. So this increases the technology complexity in process development. In the process development, there are a couple of important parameters to measure, such as critical dimensions, CD, the fin height, fin width, pitch distance, etc. And also the materials composition, the epi crystal quality, etc. These are all important parameters for process engineers to fabricate and further optimize the FinFET technology. And to obtain these parameters, accurate dimensional measurements and elemental analysis of this complex 3D structure is needed. NanoLab and Eurofins Material Science have extensive experience over the past years in analysis of FinFET. So here are our data of 22nm, 16nm, and 7nm FinFET. You can clearly see in all images, you can clearly see the silicon fin, the trench oxide, high-K metal gate, etc. We will focus on the 7nm today. FinFET is a complex 3D structure. So we will do FIB sample preparation at different locations with different views for you to better understand this complex 3D. So here I show the results of STEM images of FinCut. So the cut is on this plan, and we are looking at the plan from this direction. So these are the STEM images of low mag, medium mag, and high mag. So in the high mag image, you can clearly see the silicon atoms, the nanometer level oxide, gate oxide, and the high-K metal gate layers. At the low mag here, you can also see the metal contact, the M0, M1, etc. And from the medium mag, you can easily do CD measurements like fin height, fin width, pitch distance, etc. While we can do these measurements manually, we also the Eurofins Material Science also offers automatic measurements on CD. So the principle here is to define the interface according to the image intensity change. Then we apply machine learning algorithm to automatically optimize the interface definition and do the measurements by the computer itself. This image shows that how we achieve sub-angstrom level measurements of fin width and gate oxide thickness. And also we can get statistical analysis results. You can clearly see that the gate oxide thickness is higher near the fin tip than they are at the fin sidewalls. So this automatic measurement is not only fast and easy, but more importantly, you can see it is more reliable than manual measurements, as it minimizes the manual input. Now let's use EELS to see what these things are made of. This is an elemental map the fin structure. So you can see carbon, nitrogen, oxygen, aluminum, silicon, titanium, and hafnium. You can see that the high K layer, or this shiny layer surrounding the fin, is actually hafnium. From the color overlap map, you can see that the hafnium overlaps with oxygen here. So this shows that the high K dielectric layer is hafnium oxide. So from these color maps, we are able to achieve a sub-nanometer understanding of the elemental distribution of this fin fat. So now let's look at the gate cut. So to better understand this 3D structure. Now at this time, the TEM lamella is at this plane, and we are looking at this direction. So from this schematic image, we would expect the epi, source drain, the gauge, and silicon fin, etc. So as shown here, you can see the epi, source, drain, gauge, silicon fin, and also the STI oxide and the metal contact. You can also see some M0, M1, M2 in the low mag images. For the elemental distribution, again, you can see the hafnium dioxide high K dielectric layer and tinitride gauge and so on, which matches the previous fin cut result as cut in here. On the other hand, you can also see the germanium-rich source drain region here. And also the source and drain is connected with the metal contact shown here. Actually, as you can see, the metal contact here is cobalt instead of tungsten that we saw in previous generations of FinFET, such as 22 nanometers. One major benefit of EELS is that they can help us check elements bonding information. This is especially useful when you have a mixture of the same elements, but is bonded as different forms of compounds. Here I show an example of titanium bonded to nitrogen and silicon. So as the dimension of FinFET keeps going down, one of the biggest issues is how to ensure the low resistivity between the metal contact and the source drain. And now the industry has widely adopted tisilicide as a contact layer between metal contact and source drain. So from the view of elemental analysis, the issue is how can I analyze the tisilicide when the titanium nitride barrier layer is also in analysis region? So how do we differentiate the titanium from tinitride and the titanium from tisilicide? And we can do this by use. Here is a use spectrum of titanium LH. So the blue line is from titanium from tisilicide, and the red line is titanium from tinitride. You can clearly see an energy shift between the tisilicide and the tinitride. That is because of the bonding difference. We can use this difference to differentiate which part of this titanium is from tinitride and which part is from tisilicide, as shown here after the fitting. So now we can use this map to directly do measurements of the tisilicide layer to better understand the contact interface, to do dimensional analysis, etc. Another major technology advancement recently is the development of 3D NAND flash memory. Technical challenges to fabricate such a complex 3D structure include the quality of the metal fill in contact, in word line, and also high aspect ratio etch to etch such a deep hole, and also to the thickness and the continuity of deposited films, etc. Moreover, in the past 5 years, the layers of 3D NAND has been increasing from 32 to 96 to now we have seen some 128 layers on market. And we will see this number of layers keep going up. So as this number gets more and more, this 3D structure is getting more and more complex, and process engineers and materials engineers are facing more challenges to optimize this structure. So to resolve these issues, again, accurate dimensional and elemental analysis are needed. One major difficulty here is the sample preparation for this super big feature, up to 6 micron. So NanoLab has been deeply involved in the development of NAND process technique, and we have developed a series of methods to prepare 3D NAND type samples, both for cross-section and for plane view cut. So we will have another webinar next month focused on the application of advanced FIB, focused ion beam, from my colleague Charlene Sun. She will introduce more about sample preparation by then. But today, let's take a look at the TEM images first. So this is one example low mag image, TEM image of a 90+ layer 3D NAND structure. It is around 6 micron deep. And here are some zoom-in TEM images at top, middle, and bottom. In all of these images, you can clearly see the polysilicon channel, silicon oxide and silicon nitride layer, the barrier layer, and also the metal contact, and so on. You can easily do manual measurements for all of these features in one channel line. EELS elemental maps clearly shows that this metal word line is made of tungsten, and it is surrounded by the aluminum oxide high-K dielectric layer and the nitride barrier layer. And also you can see the silicon nitride charge trap layer and silicon oxide polluting gate, etc. We can also draw a line scan from top to bottom to better understand quantitatively what these layers are made of. So you can see the zoom-in region here, that is from here to in the middle here. So here you can see the ratio between oxygen and silicon is around 65 to 35. That is around 2 to 1. So this is silicon dioxide. Then it is aluminum oxide, nitride, then tungsten. Again, this structure is a complex 3-dimensional structure. So we did multiple FIB cuts at different locations to better understand this structure. Here I show the plan view cut of the same NAND structure at those locations. So we cut the lamella at this location, and this direction is a view direction. So putting these two images side by side, we can see the correspondence. So this metal contact is this metal line, and here is the tungsten word line or the background, dark background here, and each of these holes are the channel here. So by zooming in at this image, you can clearly see each amorphous layer. So we can measure the thickness of each amorphous layer at nanometer level. And also you can see that in plan view cut images, you have way much more data points for you to measure than this cross-section image. So statistically, you can have much more accurate analysis on the channel lines if you do plan view cut. And we can also do EELS elemental map to have a qualitative understanding of which layer is what element. And we can do semi-quantitative line scan to analyze each layer's exact composition. So from center to the outer layers, you can see here is a vacuum, then silicon oxide, polysilicon, silicon oxide, silicon nitride, etc., and then the dielectric aluminum oxide and the barrier nitride. And here is tungsten. So now you can combine all of this data together, the previous cross-section images, the cross-section color maps, the plan view TEM images, color maps, and quantitative line scan. So you will have a thorough 3-dimensional understanding of the dimension and elemental distribution of this 3D NAND structure. Now, the second case study is about oxidation of EUV reflective coatings. EUV, extreme ultraviolet lithography, is a key instrument in nowadays semiconductor industry. So it highly relies on this component, this multi-layer mirror coatings with high reflectance that can reflect EUV radiation. This kind of multi-layer mirror coatings achieve high reflectance by careful control of the material. So it usually includes the substrate quality, layer thickness, interface roughness, interface quality, and so on. And in many cases, a capping layer is needed for good surface termination and resistance against contamination, such as oxidation. So here I will discuss a case study to show how STEM and EELS can be used to help analyze oxidation of capping layer in EUV multi-layer reflective coatings. Here is a STM image of a multi-layer reflective mirror coating. This is cross-section, and on the top here is a carbon-based epoxy that we put to protect the sample material in FIB sample preparation. Due to IP protection, here we're not going to show the main elements here, but instead we name them as alpha, beta, X, and Y. But you can still see the important information that this STEM image can deliver. The 5 pairs of X and Y, each layer's thickness, the layer roughness, interface quality, etc. And also you can see there are 2 cabin layers here. One is alpha, and the other one is beta carbide, beta 4 carbon. In addition to the dimensional analysis, we can check the elemental distribution with a focus on oxygen. You can see that oxygen exists in alpha and beta carbide, and also there seems to be an interfacial oxide between alpha and beta carbide, and there are some dilute concentration of oxygen in the substrate. So here is a used line scan near the top capping interface, capping surface. You can have a quantitative understanding of the distribution of oxygen. So from the top to bottom, you can see here is a carbon. So that is from the epoxy from NanoLab. And then you can see oxygen actually forms the oxide with alpha and would penetrate into the substrate to a kind of high level at 20%. So while this combination of alpha and beta carbide does not work so well for protection against oxygen, the question is, can we use this single test to see the effect of these 2 layers on the protection against oxidation? So in other words, how did oxygen react with each capping layer? In the process of depositing beta carbide and then alpha, in which step did oxygen go in? Can we use this result to say maybe beta carbide alone might work? And we use EELS to help resolve this issue. This is the EELS fine structure of oxygen K edge. You can immediately notice a significant difference between oxygen bonded to alpha and oxygen bonded to beta. So in alpha oxygen, there are these two peaks, A and B, whereas in oxygen beta, there is only 1 peak. So we can use this difference to exclude this kind of oxygen to only analyze the effect of beta in oxygen and or do the analysis vice versa. Here is the EELS results after fitting. We excluded the oxygen from alpha. So here is the line scan. So you can clearly see that after the fitting, the alpha here is pure with 0% of oxygen. And here there was some oxygen that is from the epoxy. But the important feature here is that you can see that oxygen in the substrate is still quite strong, only slightly smaller than oxygen here. So this means that the oxygen would exist before the deposition of alpha. So even the beta carbide alone might not work. And actually, there is an oxide here at the beta surface, the beta oxide. So it shows that even this beta carbide alone is not a good candidate for protection against oxidation. And we have used EELS to exclude the effect of alpha. Now, the next case study is on the precipitation hardening magnesium alloy. Magnesium is the lightest engineering metal, so it has wide applications in industries where weight reduction is critical, such as aerospace, automotive, and consumer electronics. And we're going to talk about precipitation hardening magnesium alloys in this talk. This kind of magnesium alloy is strengthened by nano-sized precipitation particles. So in this kind of materials, the dislocations would need to either shear through or boring around these particles. Either way, they would improve the mechanical properties of the material. So it is of essential importance to understand what these particles are. So what their compositions are, what the crystal structures are, what their preferred orientation preference are. And also we need to have a quantitative understanding of these particles, like how many particles do you have in the material system, what are their volume fractions, etc. And we will use STEM and EELS to achieve both qualitative and quantitative understanding of these particles. First, here is a TEM and high resolution STEM images of this magnesium rare earth alloy after this aging condition. This image is on 112/0 zone axis of the hexagonal magnesium crystal. And this is also 112/0, and this is on 001 zone axis. So you can clearly see there are 2 kinds of particles here. One is a needle shape-like on this plan, and the other is more like plate-like on this plan. From these two high-resolution STEM images, you can clearly see that these two kinds of particles have very different crystal structures. And actually, in this one bigger particle, you can see a couple of small crystals. So you can use these images to directly analyze the crystal structures of these particles. And also use high Z contrast, the atomic number scale contrast, atomic number contrast characteristic of STEM image to help you analyze the atomic model. Better, we can do quantitative analysis with the help of EELS to better understand the precipitate particles. The idea here is to get the volume fraction of these particles. You can measure by this equation. You can measure the volume, the average volume of each particle, then times this value with the number density. And the number density, for example, for this image, equals to the number of particles divided by the area, the volume of this image. That is the area of this image times the thickness of the TEM lamella. So now to obtain this value, we need to know this thickness. So now the question is, how do we get thickness of the TEM lamella? And we can do this directly by EELS analysis. So T is the thickness of the TEM sample divided by lambda, the mean free path, which is determined by the sample material, equals to negative log of I0 over IT. I0 is area of zero loss peak, and IT is the sum of I0 and inelastic peaks. So basically, in each sample, for each TEM sample, we can do this kind of calculation, and we can get the volume fraction of particles inside this TEM sample. So we can prepare TEM samples at different stages of the aging process and get volume fractions of the particles of this material during different times of aging. And here is the result. As you can see, this volume fraction of the particles would follow the nucleation, growth, and coarsening classical nucleation model. So we can further do calculations based upon this volume fraction of the particles to get mechanical properties evolution of this material during the aging process. Now, at last, we show some case results on the complex perovskite oxide. This kind of material has wide applications, including superconductivity, solar cell, ferroelectricity, etc. In this part, I will show some examples of us doing TEM-based analysis to analyze structures of this complex oxide. First is direct observation of the atomic arrangements of this strontium tantalite. So this is the atomic model of the strontium tantalite, and these are the results. These are two groups of results, one from 1O direction, so the arrangements will be like this, and the other is on 110 direction, so we're looking in this direction, and the atoms will arrange like this. So here, these two images are high-def STEM image. So they are Z contrast or atomic number contrast. So they only show the heavy elements like strontium and titanium here. And clearly, you can see good correspondence between these two images and these two images. However, the drawbacks of this high-def is that it cannot reveal light elements, such as oxygen. But we can use ABF to fulfill this disadvantage. In ABF, you can easily see the light element like oxygen here. So if you combine the high-def image and the ABF image together, you can see they correspond very well to the atomic models, and then you can do this kind of imaging from different zoom axes of the 3D crystal structure, so you can have a thorough understanding of the atomic distributions in the crystal. And also, we can do atomic elemental mapping for the strontium ferrite. Here is an example. At last, we can use EELS to analyze defects in these oxides. Here, the sample material is strontium ferrite. This strontium ferrite usually has two kinds of phases. One is a perovskite. It has a perfect FCC structure, and the other one is a brown millerite. So you can see here that this kind of granularite crystal has two alternating layers of octahedral iron oxygen 6 and tetrahedral iron oxygen 4. So you can easily see this in STEM imaging, and also you can use EELS to analyze these layers by looking at the chemical bonding difference. Here shows the oxygen K edge of this oxygen 4 and this oxygen 6 layers. You can see the difference in relative intensity between this peak and this peak, representing a change in oxygen bonding. Such information can be used to help you identify the interfacial layer between PV, this phase, and BM, this phase. And also note that these two spectra are extracted from these two single atom layers. So this is just an example, but you can see that how EELS can be used to understand chemical species difference in single atom planar features such as stacking fault or dislocations. Now, at last, I will give some summary on the strengths and limitations on EDS and EELS and their respective strengths and limitations. First, here today, the EDS and the EELS we talk about are all based on TEM. So they can give sub-nanometer resolution. So this is especially useful if you are looking at super ultra small features such as semi-nanometer FinFET. And also the analysis area of EDS and EELS are around a couple of nanometers. So again, if you're looking at small features, this is very useful. The limitations of EDS and EELS is that first, the chemical sensitivity is around 1 atomic percent. So if you're looking at something really at dilute concentration, or you're looking at some like doping elements, then you might want to consider some other elements, some other analysis such as SIMS or XPS or atom probe tomography. The analysis area, again, is around a couple of hundreds of nanometers. So if you're looking at something kind of big, like at micron level, you want to do like SEM EDS. And at last, both of them are TEM-based techniques. So whatever restrictions applies to TEM would be applied to this EDS and EELS as well. So that means that the analysis are done on TEM lamella, around 100 to 15 nanometers thick. So if your sample cannot do TEM lamella, then we're not able to analyze it. And then the sample material should be able to withstand the electron beam damage, should be able to hold a vacuum environment, etc. And also here we have discussed the comparison between EDS and EELS as shown here. Some take-home messages. First, the EDS and EELS here are TEM-based elemental analysis techniques that can provide nanometer level measurements, elemental analysis. So some unique advantages of EELS include that EELS is especially useful for light elements such as lithium or boron or carbon, nitrogen, etc. It has less artifact compared to EDS, and it is bonding specific. If you want to analyze some complex compounds with different bonding informations, then you want to do EELS. And it can also help to analyze TEM sample thickness, etc. EDS and EELS, they have wide applications in a wide range of industries, like smartphone IC development, metallic alloys, complex oxides, etc. And nanolab technologies and the EAG laboratories, together we are the Eurofins Material Science. We are experts in this analysis, and we provide our customers high quality data with fast turnaround time. Now, some complementary techniques. The TEM-based EDS and EELS is here. So you can see that the chemical sensitivity is relatively higher, only around up to 1 atomic percent. So if you are looking at something smaller than this amount, you want to go check with atom probe tomography, which gives 3D analysis, three-dimensional analysis of the chemical distribution at atomic scale. And you may want to try SIMS, which is more like a plane surface analysis, but it can give a much higher chemical sensitivity. And also, the spatial resolution of TEM-based techniques are kind of small, so the analysis area is also very small. So generally, you would need techniques with lower spatial resolutions but larger analysis area to give you a better understanding, to help you get a full story of the device of interest. Now I would like to give some acknowledgement to our team at Nanolab Technologies, and also special thanks to our sister labs, EAG Kaifer and EAG Shanghai. And also we want to thank Rina and Stuart from EAG marketing team. So now some marketing slides. Why choose Eurofins Material Science? We are expert in materials analysis with extensive knowledge base and skilled expertise. We try our best to protect our customers' IP issue. And another thing was mentioning is that during this pandemic period, we are identified as essential business in all locations. So we remain open in all of our sites, although with a limited capacity. So we are still here. We try our best to still trying our best to deliver highest quality data within expected turnaround time.